Dr. Jayanta from Department of Metallurgical and Materials Engineering, IIT Kharagpur. All of you are doing very well during these trying times. So at first, I should appreciate your effort and enthusiasm to take part in this particular course on advanced materials and processes. This is simply great because you have shown your extreme interest to learn the subject. And that is one of the very major motivation for running these NPTEL courses. Now today, we are here in a YouTube live session in order to discuss your, let's say, queries during all these lecture series that is going on in online mode, and whatever you have posted in the discussion forum, and specifically for this particular live session, a Excel sheet was circulated and you have also posted many of the queries that came to your mind. Some of those queries are directly linked with the scientific aspect of this subject, and some of them are really not directly involved in this subject, but some general queries. So we are going to discuss all of them. Nevertheless, at the very beginning, I must express my sincerest thanks to all the people who are helping me continuously for running this course smoothly. The teaching assistant of this NPTEL course and the NPTEL project staff. So like many of the officers of NPTEL, for smooth running of this course must be acknowledged. Now, at present, I hope the 10th week of this subject is running. And if we look about the different weeks and the lectures that was planned or designed to deliver to you are introduction to metastable and functional alloys that was planned in week 1, and let's say bulk metallic glasses, its fundamental concept. Let's say majority of the time people all know about the ceramic glasses. Nevertheless, the metallic glasses with a metallic bonding, whether or not their properties, mechanical properties, thermal properties, physical properties, functional properties, and all these different engineering properties which come under the umbrella of all these engineering properties are interesting. And as a metallurgist, we always try to link between the microstructure and the properties, and when we need to dig out more of the science involved in the microstructure and property correlation, we really look for very fundamental physics, chemistry. And if we need to model the system, we take help of the mathematics. Okay. So without the scientific background, the basic science background, no engineering field can grow. And therefore, we as a metallurgist always try to learn more and more physics, starting from the electronic structure to the property of the atom, the diffusion, and all these basic metallurgical subjects are involved in this particular course. Now, for a glassy alloy, it is interesting that a conventional ceramic glasses are very fragile, because we can get, even though we get a very high level of strength, something like 3 gigapascal, nevertheless, the fracture toughness is very, very low, of 2 to 10 megapascal root meter. And that is why, if any of you have tried to put just a small scratch on a glass, then immediately by putting little pressure, you can break that glass, isn't it? So these are some of the very interesting phenomena. And then on the other hand, you can directly ask me, sir, what about those car? Even though people throw stone to the window of a car, it did never break actually. Yes, there are some specific treatment and laminate produced out of those glass, and therefore it can resist more shock. And there are something called thermal tempering. So these are some of the very, very important aspects of metallurgy. Now, let's move on to week 4 and week 5. There we have discussed about the shape memory alloys, pseudo elasticity, and the application. And we have backed up this whole topic with many different case studies, like nickel titanium or some copper based alloys and so on. Then we moved on to another series of high temperature materials. So therefore, we have given you a very general introduction on high temperature materials, including alloys, ceramic, and things like that. And the most promising high temperature alloys which we use in the power sector, power generation sector, or let's say some of the let's say in case of aeroplane, we use some turbine, gas turbine engines. So those gas turbine engine, a majority of the part are produced out of those super alloys. Okay, and you know that from the Carnot cycle, if we can increase the temperature of an engine, okay, and the difference between the source and sink temperature, as it increases, the Carnot efficiency increases. And therefore, these are some of the very, very important aspects of metallurgy. And then we moved on to a very, very small scale structural feature of material called as nanomaterial, and their interesting property in terms of some magnetic properties and so on. And fortunately, we are now discussing in this week in detail about the soft and hard magnetic materials. And therefore, there are some more part of those processing of those alloys, and some advanced functional alloys are still left. So please be patient. We will discuss in next 2 weeks' time. Now, I just picked up some of the very interesting questions that are asked by you. I really appreciate your effort to put these questions in the online platform. So let's move on with one after another. So here, Binu C, he has asked, sir, I have a question about what is happening in the video at 18 minutes. So lecture 34, around 18 minutes time, he has a question. However, we need to adopt a crystal selector at the bottom part of the mold. Actually, what we do here, we have a starter, and then we have used a crystal selector. What is actually it mechanically blocked drain? Yes, that's a very interesting question. Question is, sir, one seed crystal or multiple seed crystals are used? Oh no, here this is a very specific case. You please have a look at this particular figure. Okay, so then you will understand it better. So we have basically here, there are some many different crystals. Okay, so this is a seed, and then we basically have a part that you have basically mentioned where we allow them to grow into this direction. So this grain boundary should grow along the direction of the heat extraction, and therefore these grain boundaries are mechanically blocked, and only a single crystal can grow starting from the starter. So this is a crystal selector, okay? So we only select one of the crystal so that it grows, and finally at the end, so this is the crystal selector and this one is the starter block. You can see with this diagram I have shown you. So the starter block is at the bottom, which is here, and the crystal selector is looks like a spring. So this one is here, also shown here or here in different geometry you can play with, in order to mechanically block this grain boundary, and so that it should not come into the growth part. So the part that you have mentioned in the video explain how this single crystal growth can be achieved by allowing the growth of a particular grain. You can see this is a particular grain that are blocking the growth of the other grain. So they grow in a competition with the others actually. So from the starter block, multiple grain growth will happen. So however, in a single crystal growth, like a turbine blade application, when we need really a single crystal, because if we can avoid this grain boundary, then the high temperature properties will be improved. So like a creep properties can be improved, okay? So however, in the single crystal growth, like turbine blade application, we desire to have a growth of a particular crystal plane only, because there is a term we simply use in physical metallurgy, we call it as an accommodation factor. So we always, the grain will try to grow where the accommodation factor is less, means the less dense atomic planes will try to grow, okay? I can give you a simple example actually. So if there are 50 chairs in a class, and if you simply ask 10 students to come into the classroom, so they will try to be separate and try to be isolated and sit down like that. So this is a general tendency also, like the atoms, when they go and sit down and occupy some of the lattice site actually. So they always try to grow in a less dense plane actually. So we desire to have the growth of those particular crystal. Therefore, a single crystal selector is basically used. So which allows the growth of the desired crystal plane, blocking all the other crystal or their growth actually. So thank you, Mr. Binu, for your this nice question. Okay, so you have something else also. You have another question, and this question you asked, sir, I have a question. What is happening here, sir? All oxides are weaker except Al2O3. This is not. There is some artifact involved in it. Okay, so there is no question of the strength. Usually, the strength of the oxide are very high if you can make them 100% dense. Okay, so the question here, the artifact means the microstructural defect are produced during processing itself. Okay, so we need to fix the process, the parameter that's for the comparison of the strength actually. Okay, so to get a brief idea, I request you to refer to the following test and the reference actually. So in the bottom here, you can see this is Loam et al. In Journal of Material Science. This is a 2019 paper actually I have cited. Okay, so if you simply pause this video and then simply go through and search for this literature, you will get it. Okay, otherwise you simply ask, drop a mail, and the TA will respond to you. Now here, the zinc oxide is densified up to 97% by cold sintering, shows a characteristic of the strength approximately 80 megapascal, estimated by 3-point bending. However, the further 15%, okay, nano zinc oxide reinforced with ultra high molecular weight shows a compressive strength of 82 megapascal. On the other hand, the aluminium oxide is a ceramic with a properties suitable for coating material, so electrical insulator with a compressive strength of something like 2.6 kilopascal actually. So this is very very high. So not that aluminium oxide is very weak actually. Okay, and that is why this particular alumina composite people basically like to produce actually. Okay. Okay, so disperse strengthening composite, or disperse strengthen composite, and that is the interesting part actually. Okay, so we can further thank you, Binu, for your nice question, and we can move on to the another question. So here, Swarnali Paja has asked that, sir, I want to know the glassy material, its structure, and how it will change to the crystalline. So your question, I guess, was answered also in the last live session, but since I didn't get any response from you, that is why I am repeating this particular question in this live session. So the structure of the glassy material are amorphous. So atoms are arranged in a random manner. So glassy material do not have any long-range periodicity like the crystalline structure. But if we simply heat or raise the temperature of a metallic glass, ideally the crystalline phase will appear after passing the glass transition event. So glass transition event is a pseudo second order phase transition. And after that, actually, this is the TG defined as the glass transition event. And after that, there is a TX. So here crystallization will occur. And after that, the melting will occur. Okay, so for further study, you can simply go through this book of Professor Inoue and Surya Narayana on bulk metallic glasses, published by Taylor and Francis. There is a second version of this book published in 2017. So I guess you are satisfied with my answer. So let's move on to another question, which was asked by another of your friend. So, so he basically asked that, I have a question about what is happening in the video in 15 minutes. Professor, so would you like to say that the metastable is a stable condition, it is necessary to pass the unstable condition, and is a reason why it is not easy a metastable material to go through a stable condition? Yes, I mean, your question is very fundamental in nature, and it's a very good question actually. Okay, I think this question I have also answered, but maybe I didn't receive your response about the clearance of your doubt. That is why I am repeating it actually. So yes, you are very correct. Okay, so the metastable material remain in a stability. All material actually, whatever you see, they can go to a stable state or more stable state, or go to another metastable state, but there is some kinetic barrier in between. So that is explained in this particular diagram, that let's say if this one is a metastable state, we can go to another metastable state which is has a, let's say, a mega basin. Okay, so from a thermodynamic point of view, actually we have to pass or bypass this kind of activation barrier, which we call it as a saddle point configuration. So this is the energy landscape, and this image I have taken from Fan et al. And there are a lot of research work is going on along this direction to explain the metastability in the materials. Okay, so the metastable materials can be defined as a equilibrium state, but relatively in an unstable condition. Okay, so unstable doesn't mean basically that condition is a saddle point, but it is in a higher energy state actually. Okay, so therefore in the thermodynamic condition, a system becomes stable if there is a small fluctuation and need a driving force. So this saddle point configuration, when we talk about, it can go to either in the left side in a metastable state to another metastable state. Okay, so it completely depends on how you encourage the system and how you provide the extra energy. So hence it is required that the driving force is maybe large enough. So if I have a very large driving force, then this becomes basically a metastable with a greater level of stability actually. So this is something interesting. You can go through this Nature Communication publication, came in 2017. So this is one of the interesting part of this question that you have asked actually. And there is another question one of your friend asked. Okay, he is Shania Madi. Is a faculty member, and so the question is that the bonding between the layers of graphite is okay. So your question is, what is the bonding between the interlayer actually? So you all know that if I have a graphite and if I simply take away one layer of this, we call it as a graphene. Okay, so graphene is a very interesting research topic these days. Okay, so there are many people, many scientists are working very hard in order to explore all these functional properties of graphene. Okay, so now the question is that there is a covalent bonding between the carbon atom if you simply look at one of the hexagon actually. Okay, so but there are layers. Okay, in case of your graphite, there are many layers actually. I mean, this is the same we use as a pencil, okay, in our childhood days, or even today also we use actually, and therefore, so we take out this or layer by layer, which basically help us to write actually. So now the bonding between this layer are basically some weak van der Waals force actually. That is why we can write actually. Otherwise, if they have a very strong bonding, we never able to write using a graphite actually. So the interconnected hexagon or the one carbon atom in each vertex actually, the bonding within the layer is covalent that I already said, and on the other hand, the bonding between the layer of graphite is a van der Waals or weak bond actually. So you can go through this particular book. I suggest this is from Bolak books on nanomaterials and introduction to synthesis properties and application. So this will be a very nice book for you to consult actually. So with this, I think there are another 1-2 questions. So we can look at what are the questions of your other friends has asked. So one question from Himanshu Gupta, who is also a faculty member, is asking topics important for the GATE exam point of view in the material science. Professor Gupta, I sincerely request you that this is a platform where we are discussing science. The name itself says that National Program on Technology Enhanced Learning. So this it's a national mission and program so that we can use this kind of digital platform and can the science or the understanding and the engineering fundamentals can reach to a person who is sitting in a very remote place. So only with the help of internet he or she can study. Okay, and this is the name of the project. We call it as NPTEL, NPTEL. And here, this particular course, Advanced Materials and Process, is also designed to make a quality improvement program. So that is why almost like 50% of the students who are listening these lectures are all the faculty members of different institutes actually. Okay, so despite the regular students, okay, so this is the beauty of this subject actually, because every time you don't get a whole summary of these advanced materials actually. So and we are not at all concerned, and let's say we are not at all interested for some specific topic of some specific exam. Okay, so I am very sorry that you have to consult something else for that. Okay, not in this platform. Okay, so I hope I am able to answer your question. And then there are other friend who has also asked some question. The question is said, please give me a suggestion for doing research in this area of advanced materials. So that is also a very interesting question. I really appreciate that you are thinking about and looking for some direction of research in advanced material. Whatever the topics that we have discussed or we are going to discuss in another 2 weeks time, that are very much interesting. Okay, so all the topics I have incorporated to teach this subject or what you are learning are interest on today. Okay, and you can see them because all the references, the literatures, they are within last 5 years only, right? So that you have already noticed. So all of these topics discussed in this subject are of interest in today's scientific academic field, and therefore you can pick up any topic and can perform research. However, if you need any further guidance, or if you have not performed, or if you are interested for some specific areas, then please, you are always welcome to join our team. So we have a website. This is www.facwave.iitKJP.ac.in/tilde/j-/mfm/welcome. So if you simply just pause this video and then simply go to this website, you will find this particular web page on Metastable and Functional Materials Laboratory. So the subject topic and the name of my laboratory are well connected, and I am doing research last 20 years, starting from 2001 onwards, only in this direction. Okay, so if you have any wish, then you can simply join us. Okay, so with this, I do not see any further question from anybody. I really request all of you simply post your question so that I can answer immediately. Okay, if that is the case, then we will not spend more time on that, since there is no more question. So I will say for today, we will say goodbye, and we will again appear with when we will get some more questions. So I request all of you, please type it in the discussion forum, as well as whenever there is a Excel sheet circulated for this slide program, please type your question, whatever comes to your mind. We are always ready to provide you a 24/7 assistance in every way. And in the live session, we will also clarify doubts in a more rigorous way. Okay, so with this, thank you very much. Stay healthy and stay safe. Thank you.